All right, my friends, let's take a look. Let's check for part A whether you have an indeterminate form. So let's see, 2 times 0 is 0. E to the 0 is 1. 1 minus 1 is 0. And then over 0. So you do indeed have an indeterminate form. Okay. All right, green light for using L'Hopital's rule notation with the L apostrophe H over the equal sign. All right, this would equal the limit as x approaches 0 still. And let's take the derivative of the numerator. We'd have 2e to the 2x. And the derivative of the denominator is 1. And then try direct substitution again. And we'd end up with e to the 2 times 0, which is 1. And 2 times 1 would be 2. There we go. And we're done. Okay. Part B, let's check and see if we have an indeterminate form. So on the top, we'd have 1 with direct substitution. On the bottom, we'd have -3. And guess what? We're done. The answer here, I hope it makes sense. The limit value would equal the function value in this case. And the answer is -1/3. Notice we did not get an indeterminate form. And so I want to show you, I want to use this problem as a vehicle to show you why it's so important that you check. So let's see. First, let me put, let's see. Okay, so we're going to put, this is the good bad line, okay? So don't do what's underneath the line. Anyway, so if you did erroneously apply L'Hopital's rule, you would think that the answer, whoops, let's not change the target number there. Anyway, you'd think the answer would be 1, right? So don't do that. Anyway, so there's an example to show why it's so important to check and make sure you have it in indeterminate form before you apply L'Hopital's rule. Part C, limit as x approaches infinity. The graph of natural log is a good thing to know about now. Anyway, so natural log looks like this. As x approaches infinity, your output does approach infinity. It's a slow growth infinity, but it does approach infinity. So you have natural log of x will approach infinity as x approaches infinity. And then on the bottom, you have infinity as well. So you have an indeterminate form. Okay, and then let's apply L'Hopital's rule. So derivative of natural log is 1 over x, and the derivative of x is 1. I'm just going to take a step and simplify it. Not that you especially would need to. And then let x approach infinity now, and you would get 0. There we go. And what would that tell us? It would tell us that the value of natural log of x, that it approaches is infinity so much slower than x does, that your value gets squished to 0, even though they both approach infinity. Anyway, and that kind of makes sense because graphically speaking, here's natural log. Like it's such a slow growth that at some point almost looks like it has a horizontal asymptote if you're not careful when you graph it. And then here's y equals x. So hopefully you can see kind of the end behavior. They do both approach infinity, but natural log approaches it so much slower than y equals x does that it kind of makes sense that your fraction would be very, very small in magnitude and approach 0 when you divide the two values. There we go. Hopefully that makes sense. Okay, let's see. Before we go on to the next example, we need to talk about some other indeterminate forms. Let's list them here. Okay, and some of them you're going to be like right there with me, and then some of them you're going to disagree with at first until we talk about it just a little bit, okay? So some other indeterminate forms. One is infinity times 0. And if you're like me, you at first don't like that being in the list of indeterminate things because last I checked, if you have anything 0 times, then you totally have 0. So if you look at infinity times 0 and you're like, oh, I don't need to think about that, the answer is 0 to that, then here's what I need to explain to you. We're not talking about a number that is 0. We're talking about a number that's approaching 0. And so here's the idea. Let's say that you have a number that's approaching 0, but it doesn't actually get close enough to 0 before this one gets to infinity. So let's say that this number right here gets to infinity before this second number gets to 0. In that case, your answer might be infinity because you'd have infinitely many of a really tiny number, but so your answer could be 0, or could be infinity in this case. Or let's say that your second number gets to 0 before your first number gets to infinity, in which case maybe your answer is 0, or maybe there's some like perfect combination of this one getting to 0 and this one getting to infinity, where your answer could be like 5 when you're all done. Anyway, so the point is that you don't have a number that is 0, you have a number that's approaching 0, and the rate at which that happens would affect your answer. So hopefully that makes sense. Similarly, here's something else you might not think belongs in this list: 1 to the infinity. You'll just have to remember that you're talking about like not something that is 1, but a number that's approaching 1. And so, like let's say you have this number as your base. It'll be a function of x, right, with a limit statement in front of it. So let's say you have a function of x and its value is approaching 1, but from underneath, so from like the 0.999 side. And let's say that so it's approaching 1 from underneath, and then your exponent gets to infinity, in which case your answer could be 0. Because if you take your calculator, for example, and multiply 0.99999 by itself over and over and over, you'll see the value shrinking to 0. But what if your base here is approaching 1, but from above, like a 1.0001 situation, and your exponent gets to infinity real fast, in which case your answer could blow up to infinity because you have a number bigger than 1 being multiplied by itself infinitely many times. And so your answer could be infinity. So hopefully that makes sense that this could be indeterminate. And then there's some perfect combination between your exponent getting to infinity and your base getting to 1, in which case your answer could be something finite, like positive infinite, like 12 or something. Anyway, so the 1 to the infinity is very indeterminate when it's within a limit statement. Okay. Infinity minus infinity, most people have an easier time understanding why that one would be indeterminate. It depends on which one gets bigger faster as to what you'd get. Here's a fun one: 0 to the 0. Think about that along the same lines as the 1 to infinity. So if you have a number approaching 0 here as your base, let's say that your base gets to 0 before your exponent does, then your answer would probably be 0. But what if your exponent gets to 0 before your base does? Then your answer could be 1. Anyway, so these are some other indeterminate forms. And so if you ever get anything of any of these forms, then you'd have the green light to apply L'Hopital's rule. There we go. Okay, here's the list again. All right, so for example 3, I'd like for you to see if you can figure out if it's appropriate to apply L'Hopital's rule, and if it is, to go ahead and apply it. All right, see how it goes, and then check in with me in the next video. Good luck.